What's at the edge of the universe? And what happens if we try to get there? You might be thinking, wait, how is there an edge to the universe if it's infinite? This gets talked about a lot, and people usually say one of the following. The universe defines all of space and time that exists. Well, that's one definition of universe, but is it even part of our universe if we can never interact with it? And what if our universe is very, very different beyond the edge? The universe is infinite because general relativity tells us that the universe is demonstrably flat, and therefore the galaxies go on forever. But how flat? Are you sure you measured the universe's curvature with infinite precision? And my favorite, we can never know and never test it, so it's not even a scientific question. Oh yeah? I'll science any question I please. This is space-time. Okay, sorry. Before we get carried away, let's talk about the edge or edges of the universe and what it might take to get there. In a previous episode, we talked about the size of what we call the observable universe. We even gave you a number, 93 billion light years in diameter, 46 billion in radius. Go ahead and watch it again. It'll be useful. While you're at it, we're also going to be talking about the CMB, so it wouldn't kill you to watch that episode also. Okay, let's start with that 46 billion light year number. We defined that as the current radius of the known universe. It's the distance to that blob of the CMB, the most distant thing we can see in that direction. Now, it's not 46 billion light years to that actual blob. It is currently 46 billion light years to whatever galaxy or galaxy clusters that blob evolved into, racing away from us with the expanding universe as it did. We call this the particle horizon of the universe. It's the current instantaneous distance to the most distant part of the universe that could possibly have a causal connection to us. Anything inside the particle horizon is referred to as the known universe. Now, when I say the current instantaneous distance, I mean it's the distance that you would have to travel only if the universe froze in its expansion and you were traveling through static space. In cosmology, this sort of instantaneous distance is basically what we call the proper distance between 2 points. But nothing actually ever travels the proper distance. That's not how space-time works. The shortest path in space-time is defined by the geodesic, the path of light between 2 points. Even light takes time to make any journey, so we have to factor in the time interval, especially when space is changing. To travel to the particle horizon, we need to move through expanding space. And the closer we get to our destination, the more space will have expanded over the remaining distance. How far would you have to travel? Bad news, you'd have to travel infinitely far, even if you were in a spaceship that could travel at the speed of light. Just as black holes have event horizons, so too do universes. The event horizon of a black hole is that point beyond which we can never receive information because light from that point is redshifted into oblivion. It's a boundary to the observable universe. There's a region of this universe from which we can never receive any new signal. That is, any signal that's emitted today. This is because the distance that signal has to travel to get to us will be expanding faster than the speed of light before the signal reaches us. Same thing applies to our light speed spaceship. We can never get to anything beyond the cosmic event horizon because that space will be moving away from us faster than light before we reach it. Now here's where it gets weird. The event horizon of the universe is actually closer to us than the particle horizon. Given our best measurements of cosmological parameters, we think that the cosmic event horizon is around 16 billion light years away. This means that there are galaxies that we can see now that we could never reach or even communicate with. We're sort of seeing ghost images from outside the part of the universe that we could ever interact with. As our universe expands, more and more of it will cross the event horizon, and eventually almost all of it will be lost to it forever. Kind of sad, really. Of course, all bets are off if we can break the cosmic speed limit, so let's do just that. There's no doubt that Einstein was right in setting that limit for objects moving through space, but two regions of space can have superluminal relative speeds. That's actually the motivation behind the warp drive, which we might get to in a later episode if you're up for the challenge. But for now, let's just assume we have a nice Alcubierre-class warp ship and we burn the mass energy of entire stars to chase the particle horizon. What do we find? Almost certainly, just more universe. Bummer. Remember, the particle horizon is just defined by the limit of our current view. Move to my left, and my observable universe moves with me. Wait a minute, and my particle horizon expands. Travel to the particle horizon instantaneously, and you'll see the Milky Way as a cute baby CMB blob on your new particle horizon, and presumably, a pretty similar distribution of galaxies and clusters all around you. But what if we keep going? What's far beyond that edge? Well, that all depends on the geometry of the universe. On the largest scales, the geometry of space-time is very flat. It's lumpy on small scales due to stars and galaxies, but smooth on large, sort of like ripples on the ocean. Measurement of the distribution of galaxies and the CMB confirm this flatness with very high, but not infinite, precision. If space-time really is perfectly flat, then with the most simplistic application of Einstein's equations, we get that the universe is infinite. Now, people claim this a lot. So, if it's true, what happens if you cross the particle horizon? The universe just goes on and 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 on, and infinity is its own amazing beast, and there are many types of infinity, including some that involve infinitely repeating versions of this bit of the universe. But is our universe really perfectly flat? Think about it this way. The surface of the Earth looks pretty flat to us because we really can't see the curvature locally. But get some perspective by taking a ride on the International Space Station, and it's clearly curved. What if the curvature of the universe is so small that we're just not seeing far enough or measuring precisely enough to detect it? It's very possible that the universe has curvature just inside the uncertainty range of the best measurements to date. If that curvature is positive, then it may be that the universe is really the surface of a hypersphere, the 3D surface of a 4D sphere. In that case, our warp ship would eventually travel all the way around this curved hypersphere and get back to where it started. Okay, so how far would it have to travel? Based on a recent estimate of the minimum radius of curvature of the universe, you'd need to travel an absolute minimum of 18 times the distance to the particle horizon to get back to where you started, assuming expansion froze for the whole journey. We also have to keep in mind that these geometries assume that we can just extrapolate Einstein's equations in the most simplistic way. In addition, although general relativity is pretty cool, it's not a theory of everything. Non-crazy ideas for the origin of cosmic inflation suggest that our universe may just be a slowly expanding bubble in an exponentially, infinitely inflating multiverse. Now, bubble universes may be finite in size, regardless of internal geometry, and so they may have a true edge. But what's on the other side? Are the laws of physics or even the number of dimensions the same? Tell us what you think in the comments. We'll cross that edge into the multiverse in another episode of Spacetime. Squishina and others ask whether it's contradictory or circular to use Einstein's theory of general relativity to prove itself. Well, the only way to test a theory is to use it. However, you're right in thinking that just one prediction is not enough. A model has to make multiple independent and accurate predictions to be accepted as a theory. And there are few theories with as many independent and accurate predictions as general relativity. For example, the predictions GR makes for planetary orbits can give us a mass for the Sun. And that mass predicts the deflection angle for light passing the Sun perfectly, that is, its gravitational lensing effect. Same with galaxy clusters. The galaxy orbits give us a mass for the dark matter in the clusters, and the lensing gives us a mass consistent with this. ShadowMax889 asks why stars and planets aren't filled with dark matter. Now this is a great point. Dark matter is cold and clumpy, which means it can bunch together to form galaxies, but it doesn't interact with itself in any other way besides gravitationally. This means there's a limit to its clumpiness. To collapse completely into a star-sized object, it would have to lose a lot more energy. This is really hard unless you can interact electromagnetically. By comparison, the cold hydrogen gas that fills our galaxy clumps together in giant clouds, but then these clouds radiate light in different ways, allowing the gas to cool even more and collapse into stars. Dark matter doesn't do that, so it stays sort of puffed up. Mr. Lewis asks if we can please stop throwing monkeys into black holes. Don't worry, no monkeys were harmed in the making of space-time in any events that could be consistently assigned to our clocks at PBS. Isvazone informs us that upon winning a Nobel Prize for discovering dark matter particles, he or she would spend all of the prize money on Phoenix cases. And yeah, I guess that's cool, but I only play 1.6.